So, morning everybody. Today we're going to wrap up graphical models. And so what we're going to do is we will discuss undirected graphical models. So usually undirected graphical models would be quite well a fairly major research undertaking on their own. But yeah, there's not enough time to do that in quite the amount of detail that would be needed otherwise. So let's get back to the chicken and the egg, right? So remember what I said is that, well, chicken and egg depend on each other. And in the chicken and egg case, well, we kind of solved this problem by just realizing that the chicken doesn't lay its own egg. So in other words, there was a temporal axis, and that kind of solved it. So yeah, basically, we don't have that. However, suppose that we have a situation where we actually know that, well, chicken and egg are somehow correlated. We don't necessarily claim that we know that there's a causal connection. Maybe the connection goes both ways. But we just want to model a correlation between that. So for instance, assume that you have a web server and you have a user base. Then if your web server is really horrible, the users will go away or not come back very much. On the other hand, if you have a lot of users, they will probably hammer the web server a lot, and then the server will be slow. So in this case, it's not a clear-cut causal connection between things, right? And that is actually quite a challenge because we need to make sure that we can still model things that are correlated without necessarily knowing what causes what. Or for instance, if you go out with friends, there isn't always a clear causal connection which place you pick, right? This is essentially correlation within the group where, you all have your preferences and then some of those are implicit and not. And modeling all of that would be a nightmare. So the obvious question is, do we have a means of solving this and modeling this problem with graphical models? Or just do we have a means at all, right? So one way is to, encode things with some Clique potential, right? So in other words, I'm just assuming that P of chicken and egg is given by some function psi of C and E. And to make sure that it's properly normalized, I'll have to go and divide by the sum over all chicken and egg states. So, why would you care about this? Because you can have either this or that, right? So chicken and egg are correlated here. Maybe not quite in the way that the original chicken and egg dilemma had in mind, but anyway. So, the point is, if I have something of this form, then one way of really making sure this is a proper probability distribution is to write P of C and E equals e to the psi of C and E divided by the sum over C primes and E primes of e to the psi of C prime and E prime. Right. So in other words, all I'm doing is I'm taking my chicken and egg Clique potentials, which could be either, chicken and egg, or, roast chicken and sunny side up. And then I need to sum over all those possible states. And we all know that roast chickens don't lay any eggs, so, basically you only have the state of chicken alive and egg, or, roast chicken and omelette, right? So, here's exactly what happens. And so, this is just written out in slightly more formal ways than what I did before. This is basically the sum over all possible chicken and egg states. And I'm going to refer to this as G of psi. So if you squint at it, you realize that psi is a function, and so G takes a function as an argument and emits a number. So mathematicians call this a functional. And if you were to do functional programming, you'd already know functions are values too, right? So you see all those sweaters with that, right? So basically, it ingests the function, it evaluates the function at a few places, and emits a number. This thing is called, does somebody remember the name of this thing? Because we already had it before. Log partition function. Correct. And whoever has done physics in the past, you would have probably seen this as Z, the sum over the states. So you might have a Boltzmann distribution, and then you have this factor 1 over Z up front, which basically makes sure that, the sum over all your molecules in the air or in whatever other gas you're studying sums up to 1, is, properly normalized. That would be exactly Z. So Z has kind of a special meaning for physicists. It's like epsilon for mathematicians, right? You never make epsilon less than 0. So log partition. That's what this thing is. Okay. So let's look at exactly one of those cases. I mean, if I have a nice causal connection, I could do something like, the properties of the website depend on maybe the MySQL database and the Apache web server. And, well, what we get is that conditioned on the state of the website, we had that M and A were not independent of each other. Right? Because if I know that the site is up, I can infer something about the fact that probably both the database and the server are up. Okay. What I can also do is, I could also have a situation where maybe the website itself affects the database and it also affects the operation of the web server. Right? And I could therefore go and write P of M, W, and A to be proportional to some function phi of M and W, and some function phi, maybe phi of W and A. And it turns out that in this case, conditioned on W, M and A actually will be independent of each other. Because basically the website itself captures all the effects, how things can interact, and so this acts as a blocker. So remember when we looked at the baseball algorithm, right? We had to look carefully at the direction of the arrows, and we would actually go through the entire graph and then, work our way back and all of that. This is much easier here in directed graphical models. Because all you do is, if you want to know which, sets of variables depend on each other, you remove from the graph the variables that you condition on, and then if you have disjoint sets, these are conditionally independent of each other, conditioned on the variable that you just removed. So, in other words, in undirected graphical models, conditional independence questions are very, very easy to state. As a matter of fact, you can actually use the conditional independence statements as a means of mapping into an undirected graphical model. So when should you pick one or the other? Well, if you actually know the causal connections, this is much easier for debugging, right? On the other hand, if you don't quite know which way the connections go, then using an undirected graphical model is going to make modeling so much easier, but debugging slightly harder. Okay. So here's a, undirected graph. And so let's say I'm going to go and observe maybe this red variable here. And if I do so, then the sets of variables on the left and right will become independent of each other, conditioned on this red variable. you can actually work out this directly from the Clique potential case. And we'll probably go through that in a bit more detail. If I have these guys here, then again, I will be able to show that this bit is independent of that bit. And so you might wonder, what actually does this graph really correspond to? Well, what it'll correspond to is actually cliques. We'll get to them in the next slide. So, obviously, if I have this red vertex here, then conditioned on that, everything else still depends on each other because I still have reachability. Okay. So, yes, there is a unsuccessful girl band, but we're more interested in the maximally fully connected subgraph. Okay. Yeah. So, can somebody tell me some cliques? Okay. If you look at that, somebody has an idea of which variables are a clique. Yep.
There are only 3 cliques, which are the triangles.
Okay. Well, okay, so we have one here. We have another one there. We have another one there. And now what else? How many more cliques do we have left? Yes?
We've got 3 more. We've got the pairs on the right.
Exactly. So we have this one. We have that one. And we have that one. Correct. So, as it will turn out, that this is, well, first of all, these are exactly the cliques. And the Hammersley-Clifford theorem says that if I have a probability distribution that has full support, so in other words, if this probability distribution isn't 0 anywhere for any one of its arguments, then it decomposes into products of Clique potentials. So the Hammersley-Clifford theorem basically tells you that if I can write my conditional independence graph in the form of an undirected graphical model as what we see up there, then, and this is necessary and sufficient, this must be the corresponding joint probability distribution. Okay. The necessary part is a little bit of a pain to prove, as in it requires the Möbius inversion theorem. It's not long, but it's a little bit tricky. The sufficient part is very easy, and we're just quickly going to go through that. Okay. So assume that P of x is given by the product over some function psi c of xc. And with xc, I simply mean the restriction of x onto that clique. In other words, if I have a d-dimensional vector and I have a clique between variables 1, 2, and 4, then xc would be, for instance, just x1, x2, x4, right? And so now, let's assume that I condition on, well, let's say some variables in the clique. Okay. So, well, actually, well, then let's say condition on maybe x s, right? So all the variables. So I need to look at xc intersect with xs, right? And whenever the set is empty, well, I don't have to change anything. Whenever the set is full, then I can just kick out that corresponding term from my expression. And whenever the set is neither empty nor, well, the original set, then I'll just have to carry this around, right? So I basically know that P of x without S, given xs, is just the product over all the cliques with the property that xc intersect xs is not equal to xc, or equivalently, xc is not a strict subset, is not a subset of xs. Right? That's the same thing. Of, well, it's proportional because of psi c of xc without s, and then we have xc intersect s. Yes?
So what is x of s?
Okay, x is the random variable that I'm interested in. S is the subset of vertices that I care about. So for instance, this might be, right? So S might, for instance, be these vertices here. Right? That's S. And I've just been lazy and didn't actually number those vertices, but they could really be numbered 1, 2, 3, 4, 5, 6, 7, 8, in which case S equals the set 3, 5, 6. And so x sub s is basically just x3, x5, x6. And, well, x without that set is just all the other variables. Does that sort of kind of make sense? Yep.
And if you put the set notation in the subscript, that's the same as, so x of c intersect x of s is the same as x
Correct.
sub c intersect.
Correct. I'm just subselecting. Right. So this is just like standard index, except that now that index can contain more than one entry, just because otherwise it gets supremely awkward to write. But it doesn't mean anything particularly deep. Okay. Now, if you look at this expression here, right, you could possibly decompose that into individual groups. Basically, if you have parts of the graph that are disjoint, then I can write this as the product over parts. Thank you. So I can write this as a product over parts, and then I have basically the product of C in that part, and then I have all those corresponding psi c expressions, right? And now, since all those parts are disjoint, there are no variables that are actually in x without a s that are shared between those parts, right? So these are now functions of disjoint sets of variables. And that's all I need for independence, right? So what I've just shown is that conditioned on, let's say, for instance, those red vertices, all the remaining blue vertices are independent of each other. So that's the easy part of the analysis. The harder part is to show that if I have all those conditional independence properties, because I could just start with a probability distribution and then say, well, can I actually map all of this into conditional independent parts, to show that this thing necessarily implies, well, such a decomposition. The first ones to pose this as a quote theorem are Hammersley and Clifford. Quote theorem because actually their proof was faulty. And then Julien Bézag in 1973 or 74 actually proved it. But Hammersley and Clifford were the first ones to conjecture this to be true as a theorem. And it's one of the really key properties of undirected graphical models. The good thing is that it means that if you just go and draw up, a dependent structure of how your variables you think might depend on each other, you can immediately compile that into a corresponding graphical model. So this is very, very easy. The hard part is then actually computing the normalization. Questions on that so far? Yes?
You know, for every pair of variables, for example, whether they depend on each other or they're independent, how do we go about constructing this to be?
Okay.
Which edge do we remove?
Okay. So if you had that information just for every pair of variables, this may not do you much good. So, for instance, you may have the case. Okay, let's actually take. Well, let's take the case of just the left part of this graph, right? So if I just knew the independence for every pair of variables, well, for instance, I wouldn't be able to figure out whether I have a complete clique here or not. Because, well, for that you would need to know all the conditionings. Basically, unless you were to condition on just 2 or on 2 and 3, you wouldn't know how to do it. Okay, so what you actually need is for larger sets than that. But basically what you do is if you have this conditional independence properties, then you go and construct a graph that reflects this, where now separability in a graph is now equivalent to basically removing the vertices means that the corresponding parts in the graph must not be connected. And that basically eliminates sets of variables.
So in directed graphs, you said that you have several representations that correspond to the same physical model.
In this case, no. So for undirected graphical models, there's only really one that you get. So if I have the conditional independence properties, then I get the graph. And from the graph, I get the conditional independence properties. That's it. Of course, you can have random distributions that have more such things than what you would necessarily imply just from an undirected graphical model, right? So there's no guarantee that reality may not be even simpler than this model, which is one of the reasons why, for instance, undirected and directed graphical models are not supersets or subsets of each other, right? So they model slightly different sets of probability distributions, but they are both very useful ones. So for instance, in some case, you might very well want to use copulars. So this is something that in financial mathematics is very popular, in which case you make some certain factorization assumptions on the cumulative distribution functions. And then there's something that's called principal vines, V-I-N-E, which is basically the extension of what you get from copulars. So this would be a perfectly legitimate alternative way of modeling distributions. Which one you pick is essentially a matter of course, you should pick the one that fits the data best. It also is a matter of, well, which one you're most familiar with, and also for which you have inference algorithms available. So it's a little bit of a matter of taste. That said, of course, there's the objective criterion of which one fits your data the best. But ultimately, you're probably going to pick one or the other depending on what you feel more comfortable. Okay. Okay. So any more questions on that so far? So the brief summary of, should you pick directed or undirected graphical models? In one case, you get a very nice causal description because you basically have the parent causing the child. The normalization is automatic. So basically, you don't have to worry about actually computing a normalization before you can do something useful with it. It's fairly intuitive. But it actually does require not just knowledge of dependencies, but also of which way those go. But conditional independence is still tricky. So, I mean, remember the baseball algorithm and the explaining away and the fact that if you observe the joint outcome, then the parents become dependent and stuff like that. So it has a couple of snags in terms of how intuitively you can deal with it. Undirected models are typically a little bit more forgiving in terms of, getting the causal direction wrong. So, for instance, if you don't know whether the air conditioning causes the temperature or whether the temperature causes the air conditioning, right, then an undirected graphical model should be your method of choice. If you know that the air conditioning will actually cause the temperature to change, well then, yeah, you should probably pick a directed part. Mixing them is kind of awkward. You can do some of it, and that's definitely way beyond the scope of this class. It's fairly easy to model things. Normalization is challenging sometimes, but we'll look at exactly how to do it. As a matter of fact, all the message passing algorithms that we did before for undirected graphical models just carry over verbatim. It's just that now we have different functions, but the things that we do with those different functions are identical. This is why, despite those two things being very different statistical models, most of the papers that are published in one area apply to the other one as well. So this is why you have conferences on just graphical models as opposed to conferences on undirected or on directed graphical models. Okay. So the point is, exponential families are actually amazingly useful if you want to deal with this. So remember, what we had is that we assumed that P of x parameterized by some theta is just the inner product between phi of x and theta minus the normalization. And that's just, what we had as the log partition function. Who recalls those things? I hope everybody does, right? This is one of the really important slides, so yeah. Now, this is effectively nothing else than just what you could use for a undirected graphical model. What you could do is, in particular, is assume that phi of x is just a set of phi c of xc. So in other words, my entire set of sufficient statistics is now a set of statistics only applied to the subsets of those variables. Okay. In which case, this might actually help quite a bit. So let's look at a Gaussian graphical model. So this might actually explain things quite nicely. So remember, in a normal distribution, what we had is P of x is given by 1 over 2 pi to the d over 2 sigma e to the x minus mu transposed sigma inverse x minus mu. Okay. So that's normal distribution.
It's also
Minus 1/2, yes. Absolutely.
the determinant of sigma and normalizer, shouldn't that be the 1 to 1/2 as well?
That's a good idea. Yes. Absolutely. Thank you. Yeah. So, the thing is that if I have this, I can now, treat this as an undirected graphical model. So let's rewrite the variables a little bit. Actually, let's just ignore this. And let's call this matrix here maybe gamma. And let's set mu equals 0. Setting mu equals 0 is very easy. All I do is I just shift x over to mu, and then everything's good. So in other words, what we have is, we have that this is proportional to e to the minus 1/2 z transposed gamma z, and I just made this transform. This equals, this thing here is z. Right. Okay, good. So nothing special has happened yet, but now we can immediately realize that this is, of course, now just a function of I less than j of zi zj gamma ij plus 1/2 sum over I gamma ii zi squared. And we of course have minus of all of this and the exponential around it. Okay. So that's still pretty simple. But now let's assume that this gamma is actually sparse. Because so far, if gamma is fully connected, if it has all non-zero entries, then well, that's just everything depends on everything. But now let's assume that gamma actually happens to be sparse according to a graphical model. Let's say we have something like this. Then 1, 2, 3, 4, 5. Then the corresponding matrix would be one of this form. We'd have, of course, we'd have something here. These are the diagonal terms. And then we would have something connecting 1 and 2, something connecting 2 and 3, something connecting 3 and 4, 4 and 5, and 5 and 1. Yes. So that's what our matrix would look like. And you can see immediately from that if I were to eliminate some of the variables, right? Let's say, for instance, suppose I were to eliminate number 2 and number 4, then we would basically end up crossing out these parts from the matrix. And what you're now left with is something that couples 1 and 5, all right? And something that just has the variable 3 independently of each other. Yes?
The gamma matrix or sigma?
This is the gamma matrix. Yeah.
How do you know that?
How do you know that gamma is sparse?
How do you know that these translate into the inverse of sigma?
Well, because I just defined it to be the inverse of sigma.
No, I mean,
This is just an algebraic statement. Now, the point is more that if I have a Gaussian graphical model with this independent structure, then I can work much more easily in the space represented by the inverse of the covariance matrix rather than the covariance matrix itself. Yep.
I guess I have the same confusion. Why? So I can understand why the covariance matrix would look like that. Why would the inverse of the covariance matrix also look like that?
No, the covariance matrix may very well be dense. So in this case, the covariance matrix is almost certainly dense.
But if 1 is independent of everything other than 2 and 5,
Well, it's conditional independent. So do the following thing. Let's assume that 1 depends on 2, 2 depends on 3, 3 depends on 4, 4 depends on 5. the joint covariance matrix is still going to have some dependence between 1 and 5. Right? Because, well, through 2, 3, and 4, some of the information gets coupled. So, here's a simple case. Let's say that I have xi plus 1 equals, xi plus some epsilon I. Right? No, I don't want to have manual focus. Okay. In this case, it's very clear that I have, dependence only along a chain. It would be also very easy to write the corresponding joint normal distribution, right? Because what I will get is basically something of the form exp of minus 1 over 2 sigma squared, basically xi plus 1 minus xi squared, right? And this just so happens to be exactly our inverse covariance matrix. Because I'm assuming that, xi plus 1, depends on xi just through some noise. And so I could write out the full model this way. But that's just the inverse covariance matrix, and it just happens to be way, way easier to deal with. So in other words, when we're dealing with Gaussians, several things could happen. I could have the case that the covariance matrix is sparse. I could have the case that the inverse covariance matrix is sparse. Or I could also have cases like where the covariance matrix is low rank. And it turns out that in those cases, inference is much easier than if you have a full covariance matrix, and there are very nice results on Gaussian graphical models. Okay. So that's just as a quick aside on how the Gaussian graphical models and sparsity and undirected graphs connect to each other, at least a little bit. Okay. Any more questions on that? So, the easiest is really if you sit down at some point and work out what happens on a chain or a ring where, well, let's take the chain first, where basically xi plus 1 depends on xi. What you can see here is that if you assume that, for instance, some variable depends on the average of its neighbors, then you essentially get the graph Laplacian. Actually, we can do that explicitly. So, if I was to assume that xi depends on its neighbors in this way, that I basically have j neighboring I, xj 1 over dj, and I square this, right? And then maybe I sum over all the vertices I. Okay, so this can actually be written as x minus, well, inverse degree times the connectivity matrix times x, norm of that squared, right? Which, of course, I can write as, in this case, identity matrix minus d inverse w x. Or, in other words, I get x transposed 1 minus d inverse w transposed, and the same thing x. And so now we are pretty close to the graph Laplacian. If you were not to normalize by dj, but you would say simply, well, x minus, xj for all of your neighbors, then you would have the graph Laplacian directly. So if you took something like xi minus xj squared I neighbors j, then this would really give you just 2x transposed lx. So that's how spectral graph theory connects with undirected graphical models. To get rid of this, unsightly inverse degree, you can do that by normalizing this weighting by the degree again, and then you get the normalized graph Laplacian out of that expression. Okay. If you don't know spectral graph theory, Gary Miller teaches an awesome class on that. You should probably check it out sometime. If you did electrical engineering, you would have probably seen similar things with networks of resistors, right? This is the usual question that you torture students with. Here's a network of resistors, work out the voltages at a few locations. It's exactly that condition that you're getting. Okay. Any more questions here? Okay, yeah, good. Then let's move on with exponential families again. Okay. So an obvious thing that you can do is you can ask, well, what happens if I condition on something? And what we're going to do now is we're going to cover probably about 2 years worth of research in 2 to 3 slides by talking about conditional random fields. Okay. So when I have just p of x parameterized by theta, well, I get exactly what I wrote out before. But what I could now do is I could ask, what about p of y given theta and x? So in other words, I just designed some joint sufficient statistic phi of x and y, and I just condition on x. And all the algebra goes through. If you look at the top and the bottom of the slide, the equations look exactly the same. The only difference is, well, that pesky conditioning here, right? What I get is that the normalization depends on x, the sufficient statistics depend on x, everything depends on x. But what that is really just a conditional model. So if I want to classify, for instance, then I simply pick y to be, just plus minus 1. If I want to regress, then I pick y to be, a real number, and maybe my statistic phi of x and y to be quadratic in y, right? So this gives me as it turns out, a Gaussian process regressor. If I pick y to be a sequence of 1s and 0s with corresponding adjacency properties between yi and yi plus 1, then I get a conditional random field. So in other words, just by playing with phi of x and y, I get a huge family of models which all have their own name and all ended up pretty much being blockbuster papers. If y is a permutation, then I can actually do ranking with this. So there's a very large family of such models that I can easily deal with. So the obvious question that you need to ask yourself is, well, how can you do efficient estimation in that? Well, actually, it's fairly straightforward. It's exactly the same thing that we did already before when we looked at exponential families, just that now you have this additional conditioning variable. Before that, we just tried to model p of x parameterized by theta. Now we just use x as a conditioning variable, basically as an additional parameter, and we work on p of y given x and theta. And so the log likelihood, or actually log posterior in this case directly, is just, well, the log likelihood for each of the individual terms. Right? And then I have a prior. And so I can work out just by definition what it looks like. And then, well, I take the derivative, and there I go. Okay. So the only difference from before is, yes?
That should be summation of log of p of yi given xi theta?
That would be because things decompose. So I basically have log of yi. Yes, of course. Yeah. Yep, thank you. Of course, otherwise, taking the log of a vector is not very well defined. Yes, you're absolutely right. So there's really nothing special in there except that I have one additional variable. Now, what I can then do is I can just take the derivative because we want to optimize this. So if we want to have a maximum posteriori estimate, well, we just take the derivative, we set it to 0. Doing that gives me that last line. Okay, so now if you look at that, well, the first term is really easy to compute, right? Phi of xi and yi, that's basically your patterns and your labels. The xi is being your patterns, the yi is being the labels. The second term, namely the expected value of y given xi, is a little bit harder to compute. What this now really means is that we are asking the model, well, what do you think the y should be like given x? Right? So for instance, for binary classification, that would be just really plugging in directly p of yi equals 1 or yi equals -1 given x. And then, the last term is just our prior that makes sure that our parameters don't get too large. So what I'm really doing is I'm trying to find a set of parameters theta such that under my model, the empirical average, as in what I observe, matches what my model thinks it should be. Right? That's my observation. That's what my model thinks it should be, and that's just a penalty to keep the parameters from keeping them small. Okay. Any questions so far? We're actually going to make this rather much more concrete. Let's go back to logistic regression. So everybody remembers that, right? So what I'm now doing is I'm just setting up a rather weird label space. I'm setting up that phi of x and y is y times phi of x. I can do that. It looks a little bit weird, but I can do that. In this case, well, the log partition function is just, e to the, 1 times phi of x dot theta plus e to the minus phi of x dot theta. And that's just, log 2 cosh, so we all know that. And so now I get a very simple optimization problem. And has somebody seen this thing here before? I am sure that you have seen it before, but you probably wouldn't recognize it because it's written in a very bizarre way here. Does somebody have a guess?
Is it the logistic?
Exactly, perfect. This is the logistic. Yep. So if you massage the algebra quite a bit, you will find, and yeah, there is another bracket missing here, that it's the logistic function in this expression here. Okay. And then, well, I can easily predict. I can, estimate p of y given x and parameterize by theta. And yeah, that's basically this function. So with the exception of that factor of 2, which came from the fact that I picked as sufficient statistics y times phi of x rather than 1/2 y times phi of x, that's exactly logistic regression. Okay, so now let's be more, is everybody cool with that part so far? Okay, then let's be way more ambitious, right? Okay, yep, that actually just carries over directly for conditioning, but here's where it gets more interesting. Let's go to conditional random fields. In a conditional random field, well, what we have is we have, the y's being, dependent on maybe each other, but also on the x's. So for instance, when you do gene finding, which function a particular, k-mer satisfies has a lot to do with what its neighbors do rather than just its own structure. Because, for instance, you need the equivalent of a start and an end symbol in a genetic sequence for a certain k-mer to do something. So it's called an intron and an exon. But basically, you need to know that those things are placed on either side in order to know what this function does. Right? And likewise, in natural language processing, it helps to know that maybe named entities correlate with each other, or maybe that quite often if you have a definite article, you might not have an entity because you would say President Obama but not the Obama, right? So therefore the definite article would actually tell you that it's probably not a named entity but more just a generic term. On the other hand, if you have things like president or professor or doctor in front, then there's a good chance that you actually have a named entity. So basically, you would have this correlation between various roles in the annotation. And that's something that you can capture quite nicely by storing interactions between adjacent labels. And so, well, I can just write my phi of x to be this very long vector of, yi phi of xi. So what actually happens is that, well, I actually should have written this as phi of x and y, really. But what now happens is that, of course, this is of variable length depending on how long my text sequence is. I'm basically defining a distribution over those label sequences conditioned on the text and, for whatever length of the text that it may be. And so I get, phi of x and y dot theta is the sum over, just the xi, yi, and theta of x parts, and the corresponding adjacent parts. So this models correlation between neighbors. This just models, what comes in from the evidence. And so now, if I actually need to compute my log partition function, g of theta given x, I go and exponentiate this, but that basically means I get the product over these terms here, which now depend on yi and yi plus 1. And we know how to deal with that. This is dynamic programming 101. So we already did this in the context of directed graphical models for simple Markov chains. There's no real difference between what we did back then and what we're doing here, just that we got these functions in a slightly different form. So your code works, you just need to compute the potentials differently. Everything else is exactly the same. And, well, so that's the basically 3 to 4 slide summary of about 2 to 3 years worth of work. Well, you basically go and compute the distribution over marginal and adjacent labels. You can take conditional expectations. You can take an update step, batch or online, which is basically comparing what you observe with what your model thinks should be happening. Except that now, since you're only modeling the labels as opposed to a full density model, you're looking at only at the distribution of the labels given the data. Okay. I know this was a lot right now, but it's conceptually actually not very deep. It's exactly the same algebra, it's just that you now have a variable that you're conditioning on. Okay. So let's look at some examples. Okay. So this is something that people use to denoise images, for instance. Okay. So this model here would be as follows. You would have the red bits being the observations of the pixels on your camera or on your cell phone. The blue part is what you think the underlying truth might be. And it's a reasonable assumption that adjacent pixels typically will be of the same or of a very similar color, right? So what you're basically trying to do is, in your denoising algorithm, you're taking the red bits, you're trying to model a distribution over the blue bits given the red bits. And the problem is that this is actually not very tractable, as we recall, because, well, basically if I wanted to do dynamic programming over this, lattice here, you couldn't do it. What you can do is you can use variational methods, you can use sampling, you can use all the other techniques that we briefly discussed, but explicit dynamic programming cannot be done. So your cell phone surely does not do dynamic programming over this. But it may actually try to do variational inference. And this is then, hard-coded in in silicon. Okay, let's look at a simple chain. So, this is basically a simple chain of variables. Remember, if we want to condition on the red variable, okay, so then, what we would do is we would just, do the standard dynamic programming, working from the left to this variable, from the right to this variable, and that will give us, P of that variable. And since we don't have the luxury of assuming a priori that the entire distribution is normalized, we need to do that in any case. For a directed graphical model, I didn't have to do that, because all I would have to do is just, maybe integrate out something before. Now, if I have a conditional model, it looks exactly the same, except that now, well, I have a few more variables to carry around, so my Clique potentials look a little bit more complicated, but there's nothing terribly fancy in that. It's still a chain. Okay. And also the plate notation carries through exactly from directed graphical models, just that you don't have arrows anymore. Okay, so how would we do the dynamic programming here? Well, first of all, what you see is that, of course, P of x given y is just, this product over, all the corresponding, Clique potentials. So this way I actually managed to get rid of all the explicit y dependence. And, well, what you then do is you just do message passing as before. So you start with the left message here and the right message being 1. And then you basically just go and sum again over, message coming in from the left times the Clique potential, which is basically what couples those variables, and you get the next one. And you keep on going. Why did I keep on mentioning Clique potential all the time? Because, as we saw before, the maximal cliques are those entities within which I can have an arbitrary function dependent on all of those variables. And in that case, of course, I cannot decompose that further, so that's why they are going to be the smallest entities that I need to deal with. Here, the maximal cliques are just, pairs of adjacent variables, right? These are my cliques. So therefore, I really only get these functions here, right? If I had something that, for instance, had longer range arcs, then I would end up getting functions that would depend on this, and maybe also xi plus 2. Right? But other than that, it would be exactly the same. Now, if you do named entity tagging, then you get some considerably more sophisticated structures. And the best way is to really go to LTI and take one of their classes on an Intro to NLP, and they will show you a lot of clever tricks how to do this dynamic programming here efficiently. Yeah. If you have an ontology, again, you have this type of hierarchical structure. But in this case, essentially, if you, let's say, want to recognize animals on ImageNet, then it's probably okay if I mix up two dog breeds with each other, right? But it's a problem if I mix up a dog breed, a dog and an alligator, and it's a real problem if I mix up a dog with a car, right? So basically, depending on how far that mismatch goes, you will actually get very different types of errors, and you might actually have different labels. So for instance, you might have up here that it's an animal, maybe here that it's a dog, and maybe here that it's a poodle, right? So this is essentially how you would then assume that certain labels actually depend on each other, and you can then use the observation, the document, or the image to condition all of those dependencies. That's something that people actually do on DMOS, for instance, except that the dataset is ridiculously noisy. So this is what we had for images. You would basically assume that adjacent pixels are correlated, and yeah, forget about dynamic programming here. You can still do it approximately, and this is what you get. Right? So this is by Lee and Huttenlocher, and if you look at, this is the original image, this is the noisy version, and then if you use a graphical model, you can actually kind of recover that quite nicely, whereas if you use blurring, it wouldn't work so well. Turns out that actually deep networks are quite amazingly good for that purpose too. One of the reasons is that even though we have all those complex long-range interactions, quite often we can learn those mappings, and also given that these interactions are usually not quite that long range as in within the small context, you can do a pretty good job at inferring what has to happen. So in other words, if I change the pixel here, it shouldn't really affect this very much. And this means that the local context can help me very much actually infer what should happen at a particular location, so I can learn that directly and sidestep all of the dynamic programming. This is one of the reasons why people currently are quite excited about things like deep networks, because they help you get around a lot of the otherwise fairly costly computation operations there. There's actually a precursor to that. It's called CERN, and it does pretty much the same thing, but CERN doesn't sound as nice as deep networks, so people don't use it that much. But it's a very similar idea. Yeah, so do a Google search for that, and you might get something nice. Okay. Couple more models, and we're almost through. Semi-Markov models, I should at least briefly mention them. So here's a simple example. Suppose I want to model a traffic light, right? And the traffic light's something very simple. I mean, it has 3 states, and it just goes from green to yellow to red to green, right? And if I was to use a hidden Markov model and have a quantization of maybe 1 second, then I would possibly need a very long hidden Markov model of a very high order. Because let's assume that the green phase is maybe 40 seconds. Then I would need to be able to look 40 states back into the past in order to figure out when it's going to get red or whatever again, right? So this is a very awkward way of parameterizing long-range connections. So the question then is there something cheaper? And if you think about it, well, we don't really care about the fact that the state was green, 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 green all the way throughout, right? All I care about is that it's been green for 39 seconds. So in other words, what's a much more meaningful parameterization is the state and the duration for how long it's been in that state. Right? And so one way to work around this is to actually explicitly look at transitions that involve state duration and state value. This is what a semi-Markov model actually does. So Kevin Murphy, okay, let me see. For whatever reason it, okay. So he was the person who actually suggested semi-Markov models. By the way, he's also written a really fantastic machine learning book. You might want to check it out. And yeah, okay, dynamic programming there is a little bit harder because you now don't know how many segments you have anymore, right? So you basically now need to do dynamic programming over pairs of state and duration. The good thing is that you really only care, for instance, for a traffic light, what the state is right now and how long it's been in that state. You don't care about anything that happened in the past. So you still have that nice Markov property that only the now is really important, but the dynamic programming is more costly. But it's still much, much easier than having to have a 40th order Markov model, right? Because if I have a 40th order Markov model, it's e to the 40. Right? So in other words, you can't do it. Whereas if you have a semi-Markov model, it's just length of the state times values. That's really way beyond this class, but I just quickly want to tell you that if you have models where state and duration matters, semi-Markov models are probably the right thing to do. And then, yes, you can use 2D CRFs for web pages. For instance, MSR Beijing, they did a couple of things on that. You can use similar things for image understanding. So basically, you actually render the page and try to figure out which parts are where. As a matter of fact, rendering the page and then using that for, well, basically information extraction from a page has become, I think, pretty much the standard by now. The reason being that if you just take the HTML, some web page designer don't necessarily design the HTML for easy extraction. They just design it to look nice. And they might do all sorts of hacky things of content overwriting each other and so on. And unless you actually render the page, you won't pick it up. Okay. Yes?
What does CRF stand for?
Oh, conditional random field.
Oh, okay.
So that's what we were doing so far. Yeah. Okay, so we're at the end of graphical models. This would be easily worth a class in its own right, and you should probably take one. What we did is we looked a little bit at directed graphical models, independence, fully observed variables, what happens if we don't observe everything. We looked at undirected graphical models, Hammersley, Clifford, and so on, very briefly. We didn't actually cover the junction trees for undirected graphical models. We covered them only for directed ones. But the algebra is identical for undirected ones. So I can only recommend that you check some of those things on your own. You basically, just sit down, draw up a model, work through it, right? So this is not, it's not hard, but you need to do it at least once, maybe twice, until you get the hang of it. We looked at dynamic programming, a little bit of inference techniques. So we're kind of done with the core part of this class, actually. We will do recommender systems on Wednesday in a fairly high-level overview, collaborative filtering, user modeling, and so on. And then from next week on, it's all deep networks based on popular demand, basically. Any questions? We probably have about 5 to 10 minutes left for questions. So, questions? Yes?
From earlier incarnations of the course, there seemed to be a lot about decision trees. Will we cover that?
Okay, so decision trees. I'd love to cover them, but there is not enough time to cover this given the currently available time. There's a lot of other stuff that we left out in this context. So for instance, we left out things like bandits. We left out experts algorithms, multiplicative updates. We left out code training. We left out covariate shift. We left out boosting. So we had to leave a whole bunch of stuff out for a number of we left out a lot of VC theory. Part of that was because, well, I ended up going more slowly than I had planned to go. And that's thanks to all the questions. And I'm very happy that you guys asked the questions, and I hope that actually, helped make the class a bit more understandable. But it also meant that we got to cover less. It's just that machine learning's a lot of stuff, and I had to make some editorial choice of what to pick and what not to. For instance, we also left out spectral methods. Yes, so unfortunately, no decision trees for you this time. Yes?
Are we presenting today?
Yes, if you are ready, then come forward and present. Because we have about 8 or 9 minutes left, so that's perfect for one presentation. But I wasn't sure whether we had a volunteer this time, because last time we were supposed to have 2 and then only 1 showed up. So, okay.
Oh, good. I brought this.
Yeah, and you only have 5 minutes.
Okay.
So if you need HDMI, there's actually, yeah.
HDMI?
Yep, should work. Okay. Okay. Would you mind stopping the camera?